Welcome to the next lecture of wireless research, in which we are building upon the basic concepts of deep learning. And in this lecture, we will see a first-hand demo that how we can use Python for simple deep learning model. So we'll illustrate one example. We discussed in the previous lectures that in conventional computing systems, we used to provide data, the function, and the computer would compute the output. But in machine learning, what happens is that we provide data and output, and the computer compute what was the program, which means the data is the features and outputs are the labels. So based on feature and the function, outputs were computed in conventional programming, whilst in machine learning or deep learning we provide features and labels in supervised learning, and it identifies what is the program. So in our demo we will use an input x and we'll give it to the deep learning model. We'll also give the output. The output is nothing else but y is equal to x square, and we'll train the model to evaluate what is the underlying function. So it will identify that we are actually performing y square. So for that, what are the steps that will be involved? We'll import some libraries in Python. These are the standard libraries that we need to import before training the Python libraries. Then we'll take the data set, make our data set, the features and the labels. We'll perform one activity that I will illustrate in my Python coding. We'll define the model, we'll compile and train the model, we'll predict, and we'll also evaluate the model. The predicted output should resemble the labels. That is what our intention is. So some basic libraries, like we'll import NumPy, where all the mathematical operations takes place. For data handling I use pandas, so pandas are important. We'll use data pre-processing as and when required. From Tensorflow.Keras models we'll use sequential. So we defined the deep learning model in the previous lecture. So the artificial neurons are basically feed-forward networks that we discussed, and these will be defined as sequential models. And we'll assume that all the layers are connected, all the neurons of each layer are connected to the previous layer, and therefore the network will be dense. And we will use matplotlib to plot our outputs. So we'll take the data set. Generally, what in wireless communication, the data set is very large. So we'll generally use some CSV files to import the data. So we are using this data frame. We use pandas. We imported pandas as PD here. You can see, right? So what we will do, we'll use this read CSV command to take our CSV file, and the columns are suppose x1 and y, and we are performing x1 into x1 is equal to y. Our performance is x1 into x1 is y. So basically it's x square. From that, the read CSV can also be used to extract the individual columns. Suppose I want only first and the second column. So indices are 0 and 1. So we'll use the first two columns. The first two columns are basically x1 and x1. And similarly, the df3, we take the data using again pd read underscore CSV and use the column 2. So what is the column 2? The column 2 is basically y. So this thing is basically the features. So I will name it as features, which is df2 dot values. I will take all the values of this data frame as features, and we'll take all the values of df3, where we have only imported the last column, the column number 3. The columns are like this: 0, 1, 2, right? So this is our y, and these both are our features, x1 and x1. Next, also what we want to do, we want to define the model, and this is most important. In defining the models, we will use our basic convention that there are certain set of neurons, and we discussed that if there are two inputs, suppose, then there are two neurons right here. So the basic is that we'll use the sequential model, the feed-forward network, and we'll say that the input dimension is 2, 1 or 2, none. So this is very important. When we define our models based on our formulations, the number of inputs come here, and the number of output of the first layer. So the output of the first layer will be connected fully to how many neurons? From 1, 2 till 64, right? So we'll use 64 networks. Again, we'll use another hidden layer. So this is our first hidden layer. We'll use another hidden layer. And how many neurons are there in that second hidden layer? 32. So now we'll have 1, 2 till 32. These are all fully connected layers. And then again these will be dropped back into 16. So 16 means the third hidden layer has 16 neurons. And finally, what is the output? Remember, our inputs are x1 comma x1 and our output is 1. So only one output is there. So how many neurons are required at the output? 1. So this is the complete architecture, and this is how we define the sequential model in Python. We'll then compile. While compiling, we use some optimizers. Generally, Adam optimizer performs very good. We define a loss function based on which the back propagation takes place. So we generally use mean square error, MSE, and the metric is MAE, mean average error. Then the important thing is the fitting of the model. In prediction, we fit the model. So we give the input, we give the output, which means we give features and labels, and we run for certain number of iterations, 50. We take batch size. The batch size is the number of samples in one epoch, how many number of samples are being executed. Suppose total number of samples are 100, and if the batch size is 10, then 10 batches will be used and each one will have 10. So 10 cross 10 will become 100. So if we use less number of batches, the model, less size of the batch, which means less number of features and labels per epoch, per iteration, then the model will take more time, it will be more accurate. But if we take more number of batches, so suppose if I take the batch size to be 50, if it is 50, then only 2 batches are there. How many number of batches are there? 2 batches. Number of batches are 2 when we take batch size to be 50. If we take 10, then will be 10. We use verbose equal to 1 to see how is the model training. So it will appear at the output. And finally, we will use predict. So our sequential model is named as model. Remember, we defined model here. You can write anything, but what you write here is the model, is representing the model in deep learning. So we are again here compiling the model. Now we are fitting the model and taking its history, and we are predicting the model. So this will be model.predict, and we'll give the input x. So we'll give it x1 and x2, which is both are same, and the predicted data should be y hat as approximately equal to y hat as possible. So this is the strategy that we use. Now we will see how this can be done using deep learning. So in Python, what I do generally is that I use this spider, Python spider we use, because in a spider there is this variable explorer and I can see all the sizes of this data, which is very important. And what are the data types, and what is the name of the variable, what are the data types. This can be done in Python, and therefore I use spider IDE always. So we'll import the libraries like I imported PD to represent pandas, sequential model from Tensorflow.Keras, from Tensorflow.Keras.Layers I have taken dense, and in order to plot I have taken PLT. These are the three things. Like if you see df1 is nothing else. So what was my data set? My data set I have stored in a file which is named data_demo, and my x1, x2 and y are this. So x1 are just 1, 2, 3, 4 till suppose I have taken 200 numbers, and x1 is multiplied by x1 itself. So my second column is also a numbers 1 to 200, and what is happening here, taking multiplication of first two columns, which means this is 1 into 1 2, this is 2 into 2 4, this is 3 into 3 9. Now in wireless communication this data set is very large. So first of all we want to like if I just execute this much, you can see that what we will have is a df1, and df1 will be all those values. So here you can see these are those indices, so x1, x2 both are x1, and so this is These are the indices, and the two values are here. I've imported x1, x1, so both have been given the same name, and therefore only one is getting imported. But this is our important thing because I am using df2 and df3. So what are df2 and df3 if I run? df2 are basically the first two columns, which are our inputs x1 and x1, and the df3 is basically, if I run only this line, then df3 is basically the y, right? So what I am doing, I am taking these values here and referring them as features and labels. So these features becomes the input data and labels becomes the output. We will refer to them as x scaled and y scaled. We'll define our model. The input to the model is a dimension of 2, the output is 1, and in between we are using 3 hidden layers. First one is having 64 neurons, second hidden layer is having 32, and third one is 16. Then we named it the model as model. So we'll compile the model, and we'll then model.fit and predict on x scale data, and we will plot. So what we will I am plotting the loss, how many what is the loss as the number of epochs is increasing, and I am then plotting the predicted data to visualize how good the prediction is. I am using a very small epoch size of 50, and when you increase the number of iterations it takes more time, but it becomes more accurate. So I run this model. So what happens when I run this model? Some outputs will appear. First output is what is the model training. So you can see the training, the loss is very high because it is 1 into e to the power 8, and as the number of epochs is increasing, the loss is decreasing, but still it is very high. And as far as the prediction is concerned, you can see that the original is the blue line, which is y is equal to x square line, and the predicted value, the orange line, is a straight line, so it is not learned. I've also demonstrated this using the scattered plot, true versus predict and predicted, and you can see the red line, which is actually in this line, you can see the red is actually predicted. So the predicted line is not following it. And what is the problem? The problem is that what we are giving as x scaled and y scaled. So let us see what is x scaled and y scaled. X scaled is basically all those numbers that we give from 1 to 200 as it is, and y scale is basically their multiplication. Y scale is nothing else but their simple multiplications, and you can see the 200 into 200 is 40,000. So it is a very large number. So what is the most important thing, and I left that in blank, question mark, the step. That step was pre-processing. So pre-processing is the step in which you can see here that when we have taken our features and labels, we will use minimax scaler to x scaled and y scaled. So what we are performing is that we are transforming the features and labels into values from 0 to 1. So let us now just run this much. So if I have run this much, I will see what is x scaled. Now you can see x scaled is a number from 0 to 1, where 1 is representing 200 and 0 is representing 1. Similarly, x1, the second column, is also 0 to 1. So all these numbers are now between 0 to 1. And what about the y levels? Y scaled values are also from 0 to 1, which means that now the deep learning model has to understand only numbers between 0 to 1, and it becomes easier for the deep learning model. I am using the same, everything else is same. It is just that what I will perform, that I will declare a scalar, which is minimax scalar. I will use fit transforms. I have exported this as minimax scalar, and I will use this to define x scale and y scale. I'll use the same model. I will predict, but remember, when I predict using x scale is between 0 to 1. So predicted data will also be from 0 to 1. So if I just run this much of it, you can see the predicted data, the model is getting trained. The predicted data is also between 0 to 1. It needs to be rescaled back, and for that we'll perform inverse transform, this transformation. So original data, first of all, we wanted, because we want to compare. So what was our original data? We want to predict y, the squaring operation. So y scaled was between 0 to 1, so I am getting original data recovered using a scalar dot inverse transform, and the predicted data is between 0 to 1. I will make it using inverse transform in the original domain, that is from 0 to 40,000, and then I will completely, so I will now run all those firstly for complete 50 epochs, and after that what we will do, we will see the plots. So now you can see, first of all, what is the loss. The loss is very small, 0.175 to 0, as the 50 epochs are used, and the training. You can see the original and predicted have overlapped. You cannot even identify which one is which. In scattering plot also they are uh, basically they are merged, which means that after pre-processing the model is trained. So this is how we train a deep learning model. We just use this tool to use the Python. We firstly pre-process the data, we give it to the model, we see what are the dimensions, run for certain epochs, and we get the predicted value back. So in this way, we can train the model. We will import libraries, import a data set, features and labels. We will pre-process. This is the most important thing. Then we'll use the model definition. We'll compile and train the model. We'll predict. We will get the predicted output. We'll evaluate that what is the error that we are getting after certain number of epochs to judge what number of epochs is required. So if you have any suggestions, please write your suggestions in the comment box. And thank you. Please like and subscribe to the